Hello, I'm Jean Vandemollebroek from l'Institut des Sciences de la Terre à l'Université Savoie-Mont-Blanc in France. This is a digital training module of the Improve project. This digital training module is entitled Structure of Hydrothermal Systems. In the part one of this DTM, I'm going to give you a few examples of the structure of these systems and also describe how geophysics, especially measurements of resistivity, can help us to understand this structure. Though there's a wide variety of hydrothermal systems, some are perched on a dome, like the Soufrière of Guadeloupe in the West Indies. Some contain a crater lake, like the nice Rapehu in New Zealand. Others are very active at the surface with many geysers and hot springs in Yellowstone, and still others are a cause of severe ground deformation, such as the flagrant fields near Naples. A hydrothermal system is a reservoir composed of fracture and porous networks, where high pressure and high temperature fluids are stored, and which can be used and propagate, and which can be used for geothermal production, as in Krapla. This porous and fracture system is, by simplifying, subject to two boundary conditions: a significant heat flow at the base of magmatic or tectonic origin, and atmospheric temperature and pressure conditions at its upper surface. So it's a system heated at the base and cool at the top, with a constant temperature at the top. If we look at the structure, we see that because of the temperature condition and pressure here, a liquid saturated layer generally forms at the surface or at shallow depths. Below, there is a two-phase zone where liquid and vapor phases coexist. And then below, there is sometimes a layer of saturated vapor. Fluids in a supercritical state may be found at greater depths close to the magma. When we model the system, we can use the following equation. This is an equation in the liquid region for a closed system. So the mass conservation, the Darcy law, the energy conservation, and the state equation for fluid. And these are the boundary conditions at the upper limit of the system. In the two-phase zone, there are the following equations: the liquid mass conservation, the vapor mass conservation, the liquid and vapors Darcy's laws, and the energy conservation. Here, the vapor phase is considered as incompressible. If a porous medium saturated with water is heated from below, while the temperature at the top is kept constant here, T0, the temperature increases with depths. If the Rayleigh number is low, the regime remains conductive and no convection occurs. This is the straight line of temperature. As soon as temperature at the base exceeds the boiling temperature of the water, an hydrothermal heat two-phase layer appears here. This is a heat pipe. Steam rises in the two-phase zone and condenses here at the interface with the liquid saturated zone. The liquid descends and boils at the lower interface here. All these movements are due to buoyancy. There is therefore an exchange of latent heat, boiling here, condensation here, between the bottom and the top of the heat pipe. Because the latent heat is very high, the heat pipe is a very powerful heat exchanger. Note there is a mass conservation, here is a heat pipe. So this is a conduction regime and the convection here in the two-phase layer. The heat flow shown on the ordinate is a function of the saturation in the heat pipe. Saturation is a percentage of liquid, and the non-dimensional heat flow here reaches a maximum for a given saturation value, depending on the model, on the permeability. Above this saturation value, the system is predominantly liquid. It's liquid dominated. Below this saturation value, the system is predominantly gaseous. This is a vapor dominated system. Here's an enthalpy pressure diagram. It shows the different conditions that govern the phase of the fluid. Here for water, this is pressure and this is the enthalpy. The boiling curve here, boiling point curve, separate the saturated liquid region here from the two-phase region here, and on the other side the superheated steam region. Above the critical point at 220 bars and 350 degrees for pure water, we find a supercritical fluid region. The fluid rising towards the surface can take several paths depending on where it starts. For example, in the supercritical dry vapor zone and where it ends, as in saturated liquid zone. High enthalpy steam, which is decompressed adiabatically, will follow a vertical line and exit in the form of superheated steam. This is here, this is a high enthalpy steam, which is decompressed adiabatically here, will follow a vertical line and exit in the form of superheated steam at the surface. In the case of medium enthalpy fluid, like this one, point H, its decompression will lead to the ebullition curve in D, where part of it will condense. If the decompression is accompanied by a loss of heat, the fluid will also join the two-phase zone here, or even directly the pure liquid zone here, depending on its initial enthalpy. As an example, at Krapla, according to the model from Scott and co-author, there is an evidence of vapor-saturated here, vapor-saturated layer overlain by an acidic condensate layer. This is an example of condensation of vapor-saturated fluid that is transformed into an acidic liquid fluid. This fluid then rises and moves away both up and perpendicular to the figure here and here. At Campi Flegrei near Naples, there is abundant fluids in different phases. Just above this is a magma body, and just above there are boiling fluids here. Then, due to the drop of pressure when the fluids are rising, a layer saturated with gas is formed, and then at the surface, due to cooling to the low temperature at the surface, the vapor is transformed into liquid condensate, which can be seen directly at the surface in a fungi mud pool that we'll see later on. In the cases I'm going to present, we'll see examples where conductivity varies both with the phase change of the fluid and also with the presence of clay. So how can the structure of layers fluid in different phases be seen from electrical resistivity or conductivity? The total electrical conductivity at zero frequency, this is a DC electrical conductivity we measure with electrical resistivity tomography, is made of two terms. The electrolytic conductivity, sigma W, and the surface conductivity, sigma S. And so if we have clay, we'll increase this term of surface conductivity, but the electrolytic part can change as well with the phase change of the fluid. In Krapla, you have a lot of smectites that will affect largely the surface conductivity due to the high surface conductivity of the clay. Here we see how does conductivity vary with the phase of the electrolyte. So these are results from Roberts et al. So are plotted the electrical conductivity versus the temperature of the electrolyte. So we can clearly see the decrease in electrical conductivity as we approach boiling. Here the normal conditions 100, followed by a significant drop in conductivity as the fluid turns to vapor. Here's an example of multi-physics measurement that shed light on the structure of hydrothermal system. We are in the flagrant fields near Naples, in the volcano's main degassing zone, which is here on the Pozzuoli solfatare. This is a satellite view of Pozzuoli solfatare. We can see clearly the very acrid zone, and there are two big fumaroles here, the Bocca Grande and Bocca Nuova. So we perform electrical resistivity surveys and temperature, as well as CO2 measurement as self-potential measurements. In terms of geology, the whole studied area is recovered by tuff deposits of several tens of meters thick. So it can be considered as a homogeneous porous and fracture medium. Let's see the cross-section here of resistivity together with the map of CO2 flux, temperature map, and here self-potential map. Here's again the resistivity cross-section. This is from the master and PhD thesis of Marceau-Grèce from ISTA. So we can see the cross-section of resistivity, the tomography, is consistent with the CO2 flux map, the temperature map, and self-potential as well, and also with the surface feature, for instance, the fumaroles here. And in this case, we can interpret the resistivity variation by changes in fluid composition, gas ratio, and temperature in the porous tuffs. So we first focus on the fumarolic area. This is the place where the Bocca Grande and Bocca Nuova fumaroles are. Well, so we can see a high temperature and high CO2 flux at the surface. There is a negative self-potential anomaly that could indicate the condensate flow. And most interesting, at depths, there is a clear resistive body which can be interpreted as a a gas-dominated conduit feeding Boca Grande and Boca Nuova fumarole here. It is surrounded here and there by conductive zones that correspond to the condensate. On the side of this conduit, we see this condensate. We see a horizontal structure here, 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 and here, like a sandwich with contrasting resistivities. A conductive zone at depths, here in blue, can be interpreted as a liquid that boils and produces above a vapor-dominated zone by decompression. Here, gas, gas. Then, as a result of the cooling of temperature as we approach to the surface, as we move here, we can see a conductive layer, then we interpret as a condensate. We have evidence of this condensate layer when we dig here at the surface. This structure is very consistent with the model of white and olives, with the high chloride water, vapor-dominated zone due to decompression, then condensate zone due to cooling. And here the water table. This is the water table of the condensate. This model was proposed first by White and then modeled by Ingebrigtsen and Sauer. We'll go a little bit, we'll stay at Solfatara, but go in this area. And here we are at the center of Solfatara, the fumaroles that we saw earlier at here. So we are at the center of Solfatara, where at the surface there is a mud pool called Fangaia, where we see water with liquid, steam, and also CO2 bubbles rising at the surface here. The CO2 comes out of the surface, the vapor condenses, and produce a highly conductive body here in blue that goes down, flows down the sides. Here we consider this is a conductivity of the water. So we clearly see this liquid saturated layer that forms around the Fangaia mud pool. From the shape of this conductor, we can model the gravity downflow of the condensate here. So this is the rising hydrothermal fluid and conductivity, the condensate downflow, and find the permeability of the system, which is consistent with measurements of the tuff sample. We'll see now another example of resistivity and hydrothermal system. I'd now like to take the example of another hydrothermal system on the Guadeloupe Soufriere in the West Indies, which has been analyzed by electrical tomography by Marina Rosas-Carbajal. Resistivity measurement in this site clearly show a conductive body here in red, a very conductive body with a kind of banana shape. Here we can see on the map. This is the Soufriere Dome in '76 during the phreatic eruption. So here we see the Soufriere Dome, which receive a lot of rain, about, let's say, 10 meters per year, meteoric water. We can see the magmatic, which is the source of hot fluids at depths, and this conductive body in red here, which is interpreted as a fracture and clay medium containing fluids. Faults here in green allows a gas saturated fluid to escape directly from the magma to the surface. And on the other side, on the left of the figure, the steam condenses and feeds the acid source on the flank here by flowing laterally like this. There is also evidence here in the center of the dome, in the terrace and gully, of this mix of condensate and rainwater. So this is very similar to the Grant's conceptual model, with again these fluids, this heat pipe here, the condensate zone that flows down and feeds a chloride spring here. It should be noted that the base of the conductive layer here in black forms a potential slip plane for the dome, which represents a major hazard. This is the end of the part 1 of this DM. Thanks for your attention.